This is going to be a short video, kind of easing us into the semester for concrete technology. It's going to build off of where we kind of left off, or not where we left off, but some of the information that we covered in the soils class last spring. Going into this semester here, I just want to really briefly review three things as they're going to apply for kind of our discussion on aggregates and their role in a concrete mix design. Real briefly today, we're gonna talk about texture. We're gonna talk about specific gravity. Last semester we called it relative density, and then we're also gonna do a quick review on mass-volume relations. So this chart on the right-hand side looks familiar. We looked at that quite a bit last spring. This is from page 21 in the textbook. And on the left-hand side here are the different soil classification systems. We looked at primarily last semester the USCS, the AASHTO, and the USDA systems. The chart is organized by showing particle sizes on the bottom, descending on the left to ascending on the right, and they kind of show with these vertical separators, these vertical lines, what size diameter particle or sieve size particle separates a clay from a silt, from a sand, from something bigger. And we never talked about those something biggers last semester. We were only concerned about soils. And in soils, sands were considered a coarse soil, and silts and clays were considered your fine soils. We didn't really care about gravels or boulders or cobbles. We will this semester, so that's why I kind of wanted to refamiliarize you with this texture classifications. And if you remember, when we talked about sand, anything bigger than a 200 sieve is considered a sand, and that got pretty small. We ran a gradation analysis and looked at some of those really small powders, which they were actually still sands. But from a 200 sieve all the way up to a number 10 sieve, which you can see is about 2 millimeters in diameter size, those are considered sands in the AASHTO system. Bigger than that, we have fine gravel, medium gravel, and coarse gravel. And we'll get into that a little bit in about 2 weeks, where we get into our discussion on aggregates and their role in concrete. You can kind of see the relationship here in the left-hand diagram, just how boulders will compare to gravels, sands, and down into your fines visually. And we looked at that with some actual gradation tests. Relative density. We talked about this quite a bit last semester. The textbook kind of goes back and forth. They refer to it in this chapter, in these chapters, as specific gravity. They're one and the same. With respect to how we're going to use them, they mean the exact same thing. And if you remember what that was, it's how much something weighs in relation to an equal volume of water. I misspelled waves there. I apologize for that. So water, by definition then, has to have a relative density of 1.0. Water compared to itself is 1. So we can look at things both lighter and heavier, smaller relative densities and heavier relative densities. Air actually has a relative density compared to water. It's about 13 10,000ths of water, which is why air floats. Air forms bubbles and floats to the surface when it's in water. It doesn't matter what's in that air. Well, it does matter. It could be composed of nitrogen, carbon dioxide, oxygen. They all have slightly different chemical ingredients, but we all know them together. We breathe in them every single breath as air. Lighter than air is helium, and you're familiar with the application of helium. Here we send it up in balloons and you can make them float, because helium is down around the order of 2 10,000ths of water, almost 10 times lighter than air, which is why a helium balloon is going to float in air. And would certainly float in water. On the other side of the scale, milk. I'm doing a little promotion here for Kalispell Creamery. I support their product. I like what they do. I think they're a good business, and they produce a pretty good milk out of Kalispell. But milk will sink in water, not easily, but it does have a slightly higher relative density, about 1.03, about 3%. And we looked at this on, I think, the midterm last semester, the relative density of gold. I had you apply that to an extra credit question, I think. And gold is quite a bit heavier, has a relative density of 19.3 times heavier than water. Hopefully you remember one of those key numbers I wanted you to remember in the soils class last spring. But granite, quartz, kind of rocks, sand in general, has a relative density or specific gravity. I should be careful with my terms, be consistent with the book. Specific gravity of a 2.65. And that becomes important to us when we start to look at these block diagrams or these phase diagrams. And you might remember these from last spring. Soil is made up of mineral solids, water, and air. And we quantify that with a phase diagram down here by ordering our masses on the right, our volumes on the left. And you can see individually the mass of the soil plus the mass of the water has to equal the total mass of your sample. By definition, air has no mass. On the other side of the phase diagram, the volume of the solids plus the volume of your water plus the volume of your air equals your total volume. Because we don't know what the water content is going to be of a soil or a rock at any given time, the water and the air vary. They're variable. This line here can be quite a bit lower. If it's a really dry soil, it can be quite a bit higher if it's a nearly saturated soil. But together, the volume of air and volume of water, together we call the volume of void, because that's a void space available for either air or water at any given time. Together they give you your total volume. And these are the equations from page 6 of your textbook. Density, dry density, moisture content, void ratio, degree of saturation, and porosity. Remember, I was really particular about wanting you to make sure you use the correct units when you're expressing one of these relationships. And just as a reminder, both water content, degree of saturation, and porosity are all expressed in terms of a percentage. So after you execute these calculations, don't forget to multiply by 100 to put your answer in terms of a percentage. Only your void ratio, by definition, a ratio is not a percentage, so only your void ratio can be left as a number, an expression of one void to another. And it will be a decimal less than 1 because you're comparing a void to a solid. I shouldn't say that. You could have more voids than solid. So it'll be a number. It could be greater than 1, it could be less than 1. I want to remind you how we went about solving for these variables in the phase diagram so that you could come over here and compute these relationships. You're going to be given either an original total mass and either a mass of water or a mass of a dry soil sample after it's been dried out in the oven. We're not going to play any tricks this semester. We're going to make this fairly straightforward because you know how to do this. You showed me how you can do this last spring. Once you have the masses, then you're coming straight over to compute the volumes. That's the direction I recommend for people because I think it works best, because you can use this density relationship to help you relate mass to volume. So if we know that density is equal to mass over volume, we can re-express that relationship as volume equals mass over density. And volume is what we want to solve for right now. And that's true about anything. The volume of any object, volume x, is equal to the mass of that x divided by the density of that x. So in our diagram, remember I always said we start here with our masses, we come up, and then we come over. So I'm going to recommend that we solve for volume of water next. And the volume of water is then equal to the mass of the water divided by the density of water. Or you could re-express that as the volume of water is equal to the mass of the water divided by the density of the water in whatever units it is that you're working in. So if you're working in grams and cubic centimeters, which is what we exclusively did last spring, that's 1, because water is kind of the object used to define the terms of what a gram meant. A gram equaled the amount of mass occupied or weighed when you had 1 cubic centimeter of water. So water is kind of the standard substance used on Earth from which everything else is compared. But we're not going to be working in grams this semester. Concrete you don't order in grams. You don't even really order in pounds. You order in yards and tons. But we're going to do all of our calculations in pounds. So the relationship I'd like you to use here this semester is get comfortable using this value for your density of water, 62.4 pounds per cubic foot. So last semester you could go straight from the mass of the water, and that value, that number, whatever it is, equaled the volume of your water because you were dividing by 1. This semester your volume is going to be quite a bit smaller because you're taking that mass of your water in pounds and you're dividing it by 62.4. Next we're going to come down and solve for the volume of our solids. And again, volume equals mass over density. Volume of soil equals mass of soil divided by density of soil. That can be re-expressed as volume of soil equals mass of soil divided by the density of water times the relative density of that soil. Because, just like we looked at in the previous slide, the relative density tells us how many times heavier something is than water. So that could be further expressed as the volume of a soil or solid is equal to the mass of that solid divided by 62.4 times the relative density of that material. That material in this semester is going to be aggregates or cement. Whenever it's aggregates for these first couple weeks, or soil in a general rule, that number can be 2.65 unless you're given something other than that to use. So that's a quick refresher. If you have any questions, please post them to the discussion board on Moodle or send me a direct email. Thanks.